How do you compute areas? Well, integration is a tool, is in fact a powerful tool to compute areas of many figures. So, in the coming modules, we will go through the construction of the Riemann integral in quite detail. We will do it in quite detail. The question also arises that this integration is supposed to be reverse of differentiation. In fact, when you learn integration in school, at least when I learned integration in school, I was not defined the Riemann integral at first. I was taught that d by dx of sin x is cos x, therefore integral of cos x is sin x plus c, otherwise you will lose -1 or some such stupidity. But this is the way I was taught, that integration is the reverse of differentiation. But that completely hides the motivation behind integration. The motivation behind integration was to find areas. The motivation behind differentiation was to find slopes of the tangent at a particular point. It turns out that integration and differentiation are sort of reverse of each other, and that is called the fundamental theorem of calculus. It is called the fundamental theorem of calculus simply because it is the most important theorem from calculus, except maybe the mean value theorem. Okay. Now, since we are taking the more conceptually correct approach of first talking of Riemann integrals as areas, the question might arise, what does all this have anything to do, this notion of area and Riemann integral? Why would you even suspect that it is in fact related to differentiation in some way? Well, it's because of the following theorem. This is the axiomatic characterization of the Riemann integral. What does it say? Now, the Riemann integral is not very useful in computing the area of some arbitrary curve or arbitrary region in R2. It is completely useless. It is more useful to compute areas of figures that can be broken down into subfigures, each of which is some graph. Okay, each of which is actually the region under a graph. So this Riemann integral is used to find out the area under the graph of a function, and it's a peculiar type of area. It's not exactly the same area as what we have been talking about up until now. It is sort of a signed area, which means if you take this figure, this area will not be twice this area. The total area will not be twice this area, rather it will be 0, because this figure underneath, that area is supposed to be negative. So why we are considering areas to be negative when you come to Riemann integrals will become very clear. It makes the theory a lot simpler. Okay, and anyway you can make it compute the actual areas by doing simple things. Okay, so this Riemann integral is supposed to measure the area under the graph of a function. So this is our setup. Let a comma b be in R. A is less than b. Okay. Suppose for each continuous function f from AB to R, we can assign a number denoted I AB of f. This is just going to stand for integral integral of f from A to B. Okay, but I'm going to denote it by IAB. Note, what this hypothesis is so far saying is that given any a comma b in R and each continuous function, you can do this. In particular, if you take some other c comma d, if you take some other c comma d and c is less than d and some other function g from cd to R, you can talk about ICD of g also. So whatever closed interval you give, whatever continuous function on that closed interval you take, there is a way to assign this number which we have denoted IAB of f. Okay. So that's the preliminary remarks about the setup. Okay. This IAB satisfying, denoted IAB satisfying. So this is going to be an axiomatic characterization. So I'll have to characterize, right? I'll have to tell you what it satisfies. The first property is that if m comma m are two numbers such that m is less than or equal to f of x is less than or equal to capital M for all x in AB, then m into b minus a is less than or equal to I ABF is less than or equal to m into b minus a. Okay. 2. If C is in AB, then I AB of F is nothing but I AC of F plus I CB of F. Okay, excellent. So these are the two things that IAB satisfies. I repeat again, the way it is written, it might look as if A and B are fixed. They are not. Given any two numbers a comma b and any continuous function f from AB to R, these two properties must hold. So this is sort of an hypothesis on not just continuous functions defined on this given interval AB to R, but continuous functions defined on any closed interval in R. Okay, so please don't make the mistake of thinking that this function is defined only for this particular pair. If that were so, this won't even make sense. These two quantities won't even make sense. Okay, so before I write down the conclusion, let me tell you what these two axioms are trying to say. This IAB of f is supposed to be area under the graph. This is supposed to be area under the graph of f. Okay, what this is saying is the following. Suppose you have the x and y axis, and just for concreteness and not confusing you, let's just take a completely positive function and a nice looking one in that. Okay, then what you're doing is you're choosing these numbers small m and capital M such that small m is less than or equal to f of x is less than or equal to capital M for all x in AB. So small m could be somewhere like here and capital M is somewhere like here. Okay, so let's draw these figures from A to B. Okay, so this is A and this is B. So small m is here, so consider this rectangle and consider this larger rectangle. Okay, now look at this area. Now clearly this smaller rectangle, which I call 1, is fully contained in the region under the graph, and this region 2 fully contains the region under the graph. Therefore, if you look carefully at the axioms that characterize area, this is nothing. This is just utterly obvious. If this IAB of f indeed is measuring the area under the graph, this should be utterly obvious. Okay, so now let's look at this second property. That is also going to say the same thing. That's just saying if you break up this area into two pieces, let's say L and R, then the area under the graph is nothing but the area L plus the area R. Again, this also follows directly from the various axioms of area that we have written. Okay, so if you notice, these two axioms for the Riemann integral are just coming from some of the properties that characterize area. Okay, this is not an entire characterization of area that we are using here, just these two simple properties. Then the conclusion. So let me move back to red because we are at the conclusion stage. Then the conclusion of this theorem is as follows. Look at the function x going to I ax of f, x coming from closed AB. So what you are doing is you are taking the given point x which is there in the interval AB and mapping it to the area under the graph of f, but only till x, not all the way till b. Then this function is differentiable in AB, and its derivative is, as you can guess, nothing but f of x. Okay, so this big theorem called the axiomatic characterization of the Riemann integral just says that if you take the most primitive properties that you would expect a function that takes a given function to the area under the graph of the function, if you take the very most basic properties that you would expect, that is properties 1 and 2 that I have written here, it turns out that something like the fundamental theorem of calculus is true. This is just, if you look back at your NCERT textbooks, you will notice that this is just a disguised form of fundamental. It's not even that disguised, it's a poorly disguised form of the fundamental theorem of calculus. So what this axiomatic characterization is saying is that areas and Riemann integral, areas and differentiation are very tightly knit together. If you take the very basic properties of area under the graph, the fundamental theorem of calculus has to drop out as a simple consequence. Now, as it is, this module is gone for quite some length. I will leave it to you to process whatever I have told. I have told a lot. Please process this. In the next module, we will see a proof of this characterization and then onwards to the construction of the Riemann integral. Note, just because you say that if there is a function that satisfies something, then it's got to be, it has to satisfy fundamental theorem of calculus, does not tell you that there is such a assignment. We have not told you how IAB of f is to be computed. That will be done by a precise construction which will be done in a later module. This is a course on real analysis, and you have just watched the module on the axiomatic characterization of the area